Hello.
Hey.
Hi, Wendy. Hi, Yuri.
Yes.
Hi, Suji.
Maybe this.
Hi, Dave.
Whew. How am I doing?
Hi, Dave. Yeah.
Hi. Well, I finally just had to look at the answers. I just couldn't figure that out. Just that, I guess that one simple step that I'm not that comfortable with anyway, but the training step, it turns out that I thought you had to give the training index into the training, the data loop, the feed, not just the evaluation for starters, but and then it turns out you just give the index, not the index comma index, right?
So is that collab too?
It is. It's Colab 2, the very first training thing on the archive data set. And it was it was the 4-step training loop. And it's, it says first you feed in the data, and then you of course do the evaluation or the out. You have to do the loss. So the training loop, you just feed it data.x and the full adjacency matrix. You don't, I thought you had to feed it the training index. The data, the training data, but you don't. At least that's not in the answer that I used, which actually worked.
Could you share a screen, which question you're talking about?
All right, let me figure out how to make Zoom go away. It's always like Zoom takes over my computer, and then I can't do anything else except Zoom things. Exit full screen, move it over. Let me get my, okay, so, we did have that fellow's answers, right? That somebody shared early, and I didn't want to use those until I literally had to make any progress. So I can go back and forth. Okay, let's see. So share my screen, desktop one, which I think is that one. Then you do share. Okay. All right. So this is literally a copy, and I saved it from this guy's repo. And all I had to add was that beginning part that makes sure that we have the right versions.
Could you share the link to that? I don't actually remember seeing that share of the repo. Just paste it in the chat here if you don't mind.
Yeah, if I can get.
Just click on the URL. Yeah.
Good old. How do you get the top thing to go away? It just went.
No,
right.
no issues. I just pasted it.
Okay.
Okay, thanks.
That's fine. So this is what I was working through. Same thing, but I was working through blah, blah, blah. Okay, finally getting to I was printing out all the things because I've never really worked with sparse tensors before. So now I kind of getting used to it, understanding what they are, and how to not get too worried about them, because they obviously work like regular data objects. So I was printing out a bunch of stuff just so I could understand it. And then my, this is wrong, by the way, don't copy. I kind of had some issues in here. I didn't do this right, setting up the convolutions. I almost did, except I didn't get I think I went back. I had 1 comma. I had from 1 to number of layers minus 2. It was supposed to be just 0 to number of layers minus 2. And then, so anyway, my big hang up though was in this section, which is now I've actually, I have his solution in here, which still doesn't work. That's why I actually had to literally go back and use his copy. So let me just go over just his copy, and I won't get too muddy with my mistakes. And it's just a little bit cleaner when I can use this, the training loop. Where is it? Oh, the training loop is down here. Where is the training loop? It's in the train function. Where is the train function? Here. Okay. So yeah, I was trying to put the training index into here. And that's where I was really, it was failing, you know, obviously. So when, of course, when I look at it, it's like, oh, this is just as simple as you would expect it to be. But I'm just not able, my brain just cannot make answers happen without, you know, a lot of background. So this is where I got hung up, was right in here. And of course, when that's not right, everything fails when you actually run this. Right, you know, of course, it's basically running this, and errors will just begin to happen. So anyway, I don't want to get lost in my my hang up.
You're training using the entire data set, right? So you'll overfit, right? Because you're calculating loss on train only, but you're training with the entire data.x and the edge t.
Yeah, that's true. That's a good
so
point.
what I did here was basically do data.x subset you know, train idx, and data edge.t subset train idx comma train idx.
I contend, well, okay, so you're saying, well, you just said something, you just said the opposite. You said that,
no, so
this, you train, you said you do train on the entire data set, which is given right here.
Yeah, so currently what you're doing is you're training on the entire data set and calculating loss only on the train, right? But in the process of training on the entire data set, you're also training on the validation set and the test set, right?
Right.
And so essentially you're overfitting your model.
Okay, so you're saying that this would actually work too?
Yes, train IDX, and then data edge t, train IDX, train IDX.
Okay, I will say, I thought I was getting errors. I put this in, oops, and I got errors, but as I said, I was misattributing the errors to this when it was indeed some other mistake I was making. Yeah. Okay, so this should work as well. I mean, it'll work. I suspect the loss will be greater. It's not, because it's not, you're using a smaller data set, right?
Right.
We could prove that real quick. So the loss at the end is well,
let me see what I got.
73, let's see, 73, 72, 70. This will take a while, so I don't necessarily want to do this, but, and I don't think my my session is still running. It's been like 2 hours. But, we can try.
Make sure it's GPU though. You're going to need it.
Yeah, I have a feeling my whole thing is, well, I could, we'll see how far it gets while we're talking. But okay, so for me, that's kind of I kind of want to match my ability to just do things with new theory as it's coming along. And when there's a mismatch like that, I start to get a little bit anxious. So at least I'm over this hump, and I did run the rest of this, his answers, and it obviously ran fine. But I don't have a good feel for exactly what we're doing here, like the pooling. So now I got to kind of mix this back in with the slides to kind of get back in sync. So that's really the only progress I made, and I can tell I'm kind of slipping in my ability to keep up with the slides, because it's, there's 4 or 5 chapters ahead of where I kind of think this was kind of focused on. Or is this kind of stuff used throughout? I mean, is this the fact that we have a GCN on graph and we're doing some predictions? What was this last one predicting? That was molecule stuff?
The last one was molecules, I think. Yes, you're right. Yeah. Graph property prediction, whether it is HIV. Well, from the data set, I went into the data set thing, and it basically says it predicts whether a molecule inhibits the HIV virus replication or not.
Oh. Okay, so the atoms in the molecule are described in the graph, and this
the edge weights are the covalent bonds between them.
Okay, and this entire output was whether it responds to, or what was the
whether it wait, I'm not a biologist, so let me get it correct also. Predict whether a molecule inhibits HIV virus replication or not.
Okay, inhibits replication. Okay. Hang on, where is that? Was that this whole? Where?
It's a binary classification, basically, yes or no.
Okay, that's right. I did. That's.
Yeah.
Where did we load that model for the last part? Load. Okay.
Let me see. So
graph property prediction on.
Yeah, it's
cell. Yeah. Molecule HIV.
Yeah.
Okay, and it did say binary. That was useful. That's interesting. So these data sets have all sorts of things kind of cooked into them. Just information plus the data. Pretty interesting, and all sorts of methods to split, I guess, or indexes to split the data sets. All these little helpers. Okay. Well, that's
also the first one was, I don't know if you already know this. This is like archive. It's basically a citation network, and the task is to predict the subject area. So each of them come with a subject area classification, like CS.CV, for instance. So computer science or computer vision, CS.NLP, right? That sort of thing. And so it has apparently 40 different subject areas. And so the task is to predict one of those.
Okay. I should be able to print, what is it, data.task? Data, oops.
Oh, they have that? Nice. Okay, I didn't know that.
I don't know. We'll find out. Data, was it .task?
I don't know if there is a .task, but let's see. Yeah, so this makes
maybe
sense.
it's data set. I think it's data set .task.
Yeah.
I gotta load the damn thing.
Yeah, maybe make it into a separate cell.
Oh.
Yeah.
All right.
Yeah, I basically went into the website and basically looked.
Okay. Well, it just told me it doesn't have a, maybe that they all don't have one.
Yeah, I don't know if, yeah.
Oh, well. Run the damn thing, so it's going to fail. That's fine. Oh, well.
What are you looking for with the task?
Oh, I just was trying to, the previous one told us it was a binary task with this one we just read. Oh, task type, data set.
No, task. Okay. Try that.
Yeah.
Dot task type.
And it should be a classification, right? Or a multi-class.
Yeah. It should be some kind of classification.
So you don't define the classification type? It's kind of implicit in the model or something?
Well, no, and it's actually specifically in this data set. This data set is is just a data set created for the purpose of using in these tools.
Yeah. So the data set contains its own classification.
Annotation.
type.
Yeah, annotation basically. Yeah.
It's not just a bunch of data.
Right. It's a very helpful.
As type.
What am I just can't think.
Yeah.
Okay. That's
Multi-class classification.
Right.
Nice. Okay.
I was looking. I kept so many links. I always do that. I have about 1,000 links. One of them was PyTorch data set.
You can use that little triangle on the far right to look at all your open tabs.
Oh, well, that's a new one. Really? That little guy? What does he do?
Yeah. If you click that, it should open all your
Well,
list of tabs. There you go.
oh,
So-
sweet. Okay, I do some other tab management, but that's a new one. Very good.
Yeah, I didn't know this either. Nice. Thanks.
PyTorch. Where's the data sets? Is it PyTorch? Yeah, or is it PyTorch geometric?
Oh, what are you looking for?
The data set description of the data sets.
I think it's PyTorch geometric data set.
Open graph training set.
These guys right here. No, it's this is this just explains all these data sets that are available to read in. And so we've used the Karate Club. We used one of these, I think. And did we just pull in a different one? Which one did we just pull in?
The archive one, right? Look for archive.
Oh, okay. That was, I think, within one of the other ones.
Oh, yeah, could be.
Yeah, it was, I think it was under TUD, the one from some university.
I had one quick question. I got stuck a lot earlier on this where it was asking you to get the label. And I just looked at that guy's notebook. So the label is the Y axis or the Y property, I guess. Why is the Y the label?
That's by convention.
Yeah.
Okay.
With the independent variable. X is the dependent variable, the data, and the Y is the answer, the label.
Right. Okay.
Yeah.
And then it's a tensor. So a tensor is basically like a matrix. I mean, are we able to like look through the contents of a tensor? It just says like a tensor. Say the label is.
Well, a tensor is, based on the computation graph. It represents what values, but it also represents a forward function and a backwards function.
Right.
No, so the tensor basically is a PyTorch construct. It's just like a NumPy array, except that you can perform like gradients on it. So it holds the information about the gradient.
Right.
Yeah.
So tensor of 4 is a 4. Is it 2 by 2 or?
It's the value of the label.
That's actually just a single.
Oh, it's just like a string. Has a label tensor 4. It's just like a name. Or it's
No.
actually a tensor. That's the string representation. Right.
So,
So the label is 4, and 4 is in a tensor because it's from that PyTorch dataset.
Right.
let's see, label. Well, this actually is a get graph class. That's actually that's one we just wrote, right? Yeah. So this basically will go into the data set that we pass in
Yeah.
and
But
pull out one of the graphs.
Yeah.
And the idea is that we want to pull out the IDX graph, 0
Right.
through IDX, and there's just one of them. There's many graphs in this data set.
Yeah. So when it's many graphs, they're basically disconnected graphs as opposed to one big graph. It separates them based on, like, the difference between one graph and another is that they're completely disconnected, or is there some kind of clusters?
Good question. They obviously have different labels. They're separate for a reason, because
Right.
they actually have a, for whatever
By
the
some-
objective of the data set is, they are
Yeah.
separate by label.
Right.
Now, what they have to do with each other? Good question.
Right.
Do they share nodes? I mean, are they overlapping nodes?
No idea.
Anybody?
Let's see.
Are they all one part of one big supergraph?
Hmm.
Maybe not.
This is the enzymes data set, right?
Yeah. Of which there are, what, 600 graphs, I think?
Yeah, I think they are individual graphs. Each of them represent one particular enzyme, right? It's a
Right.
molecular structure. If you go into the geometric should tell you the PyTorch geometric data sets.
Of which one?
The one that you're just looking at, yeah, there.
Yeah.
Maybe that has the enzymes there.
Okay. Which one was it one of these? Part of the TU?
Could be the, yeah, I think it's the TU, right? Let's see how we got it. Enzymes, big data set. Big data set is GitNum classes big data set.
There it is, TU data set, the enzymes.
TU data set, yes. Okay, yeah.
Right, so,
But just enzymes, it's not listed.
well, I guess we have to kind of dive in to see what, I guess they all follow this, but here it is.
It says variety.
Yeah. Interesting, yeah. Ooh. Are we gonna ever find what enzymes is about? Let's see.
Did you, oh yeah, you're looking at data sets, right? Okay, enzymes.
And I'm in that one. I'm in this one. And, okay. Capital E. What was it called?
Enzymes.
Enzymes, yeah.
Yeah, there's-
Capital ENZYMES.
I'm
So,
looking.
yeah,
click
Ooh,
on
maybe
it.
it's not a small molecule. Maybe it's a large molecule. There you go. It's bioinformatics.
oh, it's a zip. Okay,
Okay.
all right. It
I
goes
see.
directly
So-
to a zip.
Okay. Well, at least we kind of know what it's got. Node attributes, average nodes, this many graphs, this many classes.
Yeah,
And-
so there's got 600 graphs, right? And each of them are of 6 different types. So basically, they're all
Mhm.
disconnected graphs. It's a graph prediction kind of.
Okay.
Data set.
Okay, and each is independent, and each represents
I think the molecular structure of an enzyme.
molecular structure. Okay, which we don't know much about. Like,
So there's
what are the,
six classes means 6 types of enzymes.
I'm
That's
guessing, yeah.
100 graphs of each. What would be the difference if presumably one enzyme would always have the same structure, would it not?
one
Wondering-
class
or
of
cla-
enzyme?
Yeah,
That's to
class
be-
of enzymes, most
That's to
likely.
be that's to be shown in the analysis.
Unless
right?
they're combinations of, like, those different 6 enzymes in different ways of sticking to each other or something.
Could be.
I'm not
yeah.
sure we know what the distinct. It's what's not given is what are the different classes and how were they derived?
Right.
Was that
I mean, if the classes are super complicated, then there could be hundreds of ways of combining them because they're not
or are there generally just 6 kinds of enzymes or something like that?
Right.
You know?
Actually, I found something. Maybe I'm just going to put it in the chat. So this is from Papers with Code, and it talks about the enzymes dataset. 600 protein tertiary structures. It contains basically 6 enzymes. So a protein structures 4 enzymes, I think, is what they're looking for. It just gives you a little bit of, you know.
Right.
Oh, wait, there is another one with the GitHub enzymes. This is nice. Okay. So if you follow the link there.
Trying to find the link. Where is
Oh,
the
wait,
chat?
Yeah.
Do I
Oh,
have
it's
to go
down
to-
here. That's here's
God.
another one that goes into GitHub. This is where Vikas sent out the link to the thing.
Yeah, the graph.
Yeah. So we go down to the bottom, Dave. There is a chat link. So you click on the chat, it will pop up a thing on the side.
Chat link in my window of what?
Zoom.
Zoom. Yeah.
So if you see next to the green
Got it.
share screen button, next to that there's a chat button, and then that will open the sidebar to show you the chat, the Zoom chat. It might be that your Zoom like mini bar, because you're sharing, so you see different than us. You might
Yeah,
have to kind of click the Zoom mini bar to get the chat.
Yep. Good Lord. Okay, so let me bring that up, and it opens. This is the GitHub for the enzymes data set. And,
So the PyTorch data structures, are they compatible with like NetworkX or other ways to just plot like a visualization of the graph if we wanted to see what those 600 things look like?
I do.
You could convert it to an adjacency matrix for each graph, right? And NetworkX has ways to suck the adjacency matrix in, and then you can draw it.
Right. I was going to. Is that a standard? Is access? Oh, well, of course, the data is X and the edges are edges underscore something, right? Every data set has a common methodology.
Yeah, I think you can just get the HT if you start it up with certain things. It's in our example itself, right? So if you look at the first classification one, where
the HT of a subgraph, right? One of a subgraph being data set index.
Yeah.
Right. Got it.
I think they give you something with an edge, something or other, but you can change that to an HT, which these guys have done.
Right.
Yeah.
There's edge attribute, but there isn't data dot.
So we do.
I'm looking at the wrong clip. Okay, sorry.
So we have, every time you open a data set, you have access to the X, data.x.
Right. But this is after you turn it into a convolutional network or something, isn't it?
Well, no, but you still have to, you still deal with the data set in its raw form.
Right.
It's passed in during training. During training somewhere. Good Lord. During training. Well, in this case, it's a data loader. So that's a bad example. That's another, special thing that already has your data in it, already split out and organized. But generally, you can just pass in the data, right? And the data came from data equals something right off of the load, wherever data is.
Yeah, I think for multiple graphs, you can just put the index of the graph. It should give you a graph.
I'm getting that edge attributes or edge at ATTR. I assume that's attributes. None. None
Yes.
subgraphs. So
So in this case, there is, it doesn't make sense, right? In the graph case. But if you take the, I think data 0, I think, or data x0, try that. Data.x0. Index 0, right? Data.x, open bracket 0.
Yeah. So this is the data set. This is the,
not this one. You want the graph one, right? You want the second question, the graph prediction problem.
Oh, the graph prediction problem.
The mall H1V or whatever.
Okay.
Yeah, that one. So where it gets the data set?
Model equals model. This is still. Where does it load the data set? Right after it reads it in?
Let me check.
Graph prediction. Oh, let's see.
It's been a while since. Oh wait.
Here it is, right here. Okay.
Yeah.
You can use the nav bar at the left to kind of.
God, that's a good point. I'm not used to that either. I'm not used to Colab as much. So in this data set, you get the X, and this is then the first element.
Yeah, let's do dataset.x and see what you get.
All right, dataset.x. Let's just see what if it's. Oh, what in the world? Well, let's see.
Actually, so
it should be data.x.
Yeah, probably, yeah.
Data set. Yeah, the data set's the whole thing. If you want to get the graphs, you would get. Okay, so let's try data. This should be all of the data.
Yes. Yeah. Okay. So index it with 0.
Yeah. So this will be the first element of the data set, which is the features of.
Yeah, this is the features of the
node
graph.
Of one of the nodes.
One of the nodes, yes.
Okay.
Oh, one of the graphs. Sorry.
One of the graphs. Okay, right.
And can you do help on that? Help data dot whatever. Help open brackets and open parents and yeah.
What? All right.
Yeah.
Help of what?
Whatever the previous thing was, data.x0.
What's help?
It's gives you the documentation for it.
That's a code thing.
Even of the data?
Yeah. So here it is. Go down.
Oh, it does a type. It actually knows what type it is.
Yes. So it basically returns a doc string.
Right.
But can we see, if we can get the adjacency matrix from here? That's what I'm trying to find out.
Well, it's data under AGT. You want to get literally get the whole thing out?
Can we do that?
Yeah.
Okay.
It'll probably just tell you it's a 2-dimensional.
Okay. So.
Good Lord, what was that thing?
Yeah.
Sparse tensor. Okay.
Right, but yeah. So maybe then data.agt of 0, maybe. Yeah.
Yeah, that's right.
Of the 0th element.
One of them. Yeah. So it's going to just be one side of the adjacency matrix.
Right. Okay. So let's see the shape. Dot shape or dot size. Open close. And yeah, there.
I didn't like that.
I didn't like that. Oh, dim. Okay. No, this is the bound method. So do dim equals 0 maybe, or just 0, and we can do it separately, like 0, 1, 2, whatever. 0. No, the round brackets.
Yeah.
Parents. Sorry.
Oh, you're giving. What does that do? That's.
I'm just trying to find the size of the thing. So I'm guessing it should be a 2-dimensional matrix, right? So okay, 0 size, and how about 0?
This is the
1 by 6, 9. Okay, so this is flattened. You don't want this flattened.
So the adj_t is an adjacency tensor. Is it not the adjacency matrix of the underlying graph?
It should be the adjacency.
It is,
matrix.
but it's
I wonder, I mean,
it's a tensor. The adjacency matrix is a tensor of rows and columns.
let me try running it on my own so it's easier. Yes.
Sparse tensor.
Right. Well, of size rows. Sparse tensor, right. Now, what if you just wanted one?
It's got row length,
Right.
but then that is the tensors, not just, it's not the actual graph data behind it. This is like post-processed into a tensor, is it not?
Yeah, but it is the data.
But I saw somewhere there was a transformation on that adj_t dot like to symmetric. Yeah, and under
Yes.
load and preprocess data set on section 3, it has data adj_t equals data adj_t dot to symmetric. So I'm not what it make the adjacency matrix to symmetric. I'm not really sure what that's doing.
Yeah, good point. I don't know.
Oh,
Yeah,
yeah. Okay, go ahead. Okay, sorry.
I think, isn't it that you can, because like the for an undirected graph, like you have two triangles in your adjacency matrix, and they're equivalent because it's undirected. So potentially, like maybe they're just like that they store only half of it, like one triangle, and then you and then when you actually pass to the net, maybe you need to kind of make it back into a square thing again and sparse form. Or that's my guess.
That's a good point. Like a lower triangular, and then the symmetric version, of course, is the same thing with flipped over. Is that how that? It looks like it. 0, 0.
Well, I noticed when it was get the number of edges in that example book, he just divides by 2. But can you assume that an undirected one, converting a directed to undirected, you can just divide by 2? Because if there's one-way link as opposed to a bidirectional link, you can't just divide by 2 as simply as that, can you? It's assuming that every link is bidirectional, in which case there would have been 2 for every one.
Right. I think that was done early in the class.
Yeah.
Where we did just the
Divide.
number of edges was, if it was directed, it was twice.
Okay.
Twice the number. But
I'm not quite sure I follow what you're trying to talk about.
I'm not sure either. But,
Oh, I think you can get the edge index to
is that also just
David's question, right? About printing it into a network X graph.
right?
Yeah.
You can get data set 0. It will give you the first graph, and in data set 0, it has a thing called edge index, which should give you. It's let's see. I can paste it. Hang on, let me, if I can just go back to this. Okay, yeah. So this is what I have here. So I just did a help on that, which gave me an enormous thing. So I'm just trying to now look and see what it has.
So data set 0 is one of the graphs. It has an edge index.
So it's basically 2 arrays with the source edge and the target edge. So you can use this to, either, so basically it's an edge list, right? So if you, if you look at this, right, it goes 0, 1, 1, 0, 1, 2, 2, 1, and so on, right? And
I don't-
you can construct your edge list and create a network X graph from there.
There's some kind of function in network X probably to create a graph based on a list of edges. As
Yes, yes,
a different way of representing it than
Why
a
is
matrix, right?
yes. Yeah, you'll have to create that list of edges. It takes in a list of basically pairs of tuples, basically a list of tuple of edge indexes.
Right. And that's not from data.x0. It's data.
No, a data set 0 dot edge index. Data set 0 gives you the graph. It says that if you go up one in where you downloaded the thing, the OGBG mol hive, right? So right there, it says print example graph at position 0, data set 0. Or did I put that in? Maybe I put that in.
Yeah, I don't see that.
Yeah, look for OGBG hyphen mol hive, MOLHIV.
That's loading. We loaded that right.
Yeah. Okay. And right in that area, it
Reload that. Hold on. Gosh.
Okay.
It's
I got absolutely nothing for dataset 0 edge index.
right. That's kind of what I was. Okay, this is the archive. Let's move on to the next one, which is we loaded
yeah. So
this guy. Okay.
Yeah.
And I did the same thing.
And right under this, you're not able to see it.
Right. It just right here just does not execute. It just not. It's.
Edge index.
It
I
just
get
goes
it from here.
0.
It has executed, but it's none, so you don't get anything.
Right. I'm just trying
But
to
it
wonder
should
why,
print it,
why
right?
not? Yeah. Where's the edge index for?
Yeah, this is what I get. I can.
That's that's the first graph.
Yes, data set 0 should give you the first graph.
Right. Is that
And
right?
then
Data set 0. Yeah, data set. Or is data equals data set 0. That's the graph. And why?
and
is
then
it,
if you do an edge index on that, it should give you something.
Nah,
Right.
it gives none, pretty sure.
right here, I mean, it's executing and then returning none.
I put the result
Yeah.
into a variable.
Yeah,
and
I think maybe you haven't
can-
got the right data set. You pulled the previous data set, and so if you rerun the previous thing where you load the mol hive.
It's very possible. Very possible. Maybe my Colab. Here you go.
Yeah, now run this.
No, same for me.
There.
Ah, Oh, you're on example 4.
Well, I had to reload it.
Yeah, I was running it against sample 3, a different data set. So the ArcSIF data set. So
Yeah, that doesn't have graphs, separate graphs. It's one big graph. So data set 0 gives you nothing.
Huh.
So here's the 0, 1, the 1, 0, 1, 2, 2, 1. They're in pairs, right?
Right, exactly. Yeah. So you'll have to reconfigure them to create a list of tuples and then pass it to network X, and that should be able, you should be able to do an extra after that.
Is that like a
This is direct. These are directed index, right? Because I see 2, 3, and 3, 2 both.
I
Right
guess,
here.
yeah.
3, 4, 4, 3,
Yeah,
4,
yeah.
5? They're pairwise.
Right.
Exactly pairwise. What would that be? A zip function to get those into
You could,
tuples?
yeah, I think you could, or you could do something. Yeah, I guess you could do a zip. Take the 0th entry and the first
Never
entry.
really done that much, but I almost used zip in one of my dead ends.
Okay.
Was that data set 0 dot edge? Oops, edge index. Now that's going to be a 2-dimensional. Should I do 0 and 1 like that, and then do it again? Is that how zip works?
You just paste the two together. Make sure they're the same size, and paste the two together. Let me try doing this. I usually have a better,
kind of okay with trying something once, and if it's down the wrong path, then oh, it's an iterator. How do you get the thing out? A list or something?
Next, maybe.
Let's see. Zip returns an iterator.
Oh, you can just iterate through it.
The list zip, or you can just pass the zip into whatever you're trying to make.
Yeah, you could wrap it with list, and then I think that will
Well, you know, you get the idea. I don't think it's actually working, but
Here. I can paste this again. Should. Yeah, I think you got something close, right? So here.
close. Yeah. Okay.
Yeah. So I just converted to NumPy before I do that. So that's all it is. And so it gives you like, like a set of tuples, but you can also just put it into like, you can call it edge list maybe. Hang on, I can update that as well. Edge list append.
Okay. Converted both dimensions to NumPy,
Right.
and then just zip the two together, and it iterates with S and T, and then you print it out as a tuple. Got it.
Right, right. And then you append it to a list, and that's what you pass to network X. Yeah.
Well, that's handy. That's kind of good, useful stuff. We can take, information from one of our exercises and kind of work it down to something where we can display it in a visual. That would be a really good exercise. Good stuff. Okay. Let's see. So that's I guess that was kind of one of the goals, was to kind of get to and through Colab 2. The essence of this, though, is predicting the class of these molecules, say at the end. I'm just trying to think of any other things that would be helpful going into like some of the lectures. These are what? Okay, so we're doing a graph. We're not doing node or edge prediction. We're really doing, in this case, graph level predictions.
Yes.
Using, these are actually embeddings, right? That's the part that I really had to skim through quickly because I was so tied up with the other one. These are, he actually has an embedding function.
These are feature vectors, right? So the graph that the x, the data.x here, or the data set.x, I guess, is basically feature vectors for the particular molecule.
Feature vectors of the molecule. The molecule is not the graph. Yeah. Is the molecule the entire graph? Yes.
I think it is. Yeah.
And the feature.
So I didn't look at that. Let's see now. Okay.
I did want to try to get to the point where I was here encoding. Hold on here. So you pass in pooling.
Yeah, it does have a feature vector.
Okay, each graph has a feature vector.
Yeah. And I think it's of size 9. Each node has a feature vector of size 9. Therefore, the graph, if you do this, it'll tell you what it is. Here. If you do this, it'll show you a 19 by 9, and I bet the number of indexes. Okay, let's see. Data set 0. What did it say? X is 19 by 9. edge index is 2 by 40. Okay, I think they have 19 nodes in the graph because when I did that, yeah, there would be 19 nodes. I'm not sure how to get the number of nodes. Maybe help.
So graph 0, the X
Num node.
there are 19
num nodes. Okay.
Okay. Yep. Oh, good. Okay. That's the whole data set has num nodes.
Yeah, num nodes tells you how many nodes, and you saw the X
Yep.
features. So each node has a 9-element feature vector, and
Okay.
that's the graph representation.
So the first data set, X, the third node has these 9 features. Okay. And those are what's passed into for the embeddings?
Yeah, those are the inputs, and then it gets the atom encoder does, in this case, I think the atom encoder takes that input and creates some kind of thing for you. It's a pre-trained thing, I think. It's like, or if it's not pre-trained, it's, you know, it comes from somewhere else.
Oh, some bona fide way of doing the encodings.
Right. Yeah, if you see the first import on the top in that block from ogb.graph, whatever. So that's where the atom encoder comes from. So I just took it on faith, and you know.
Right. And okay, so that this will continually encode the nodes, pass it through this GCN, which first encodes it, then oh, this is just the definition. Sorry. Okay, I got the idea of what the GCN kind of does. Then the pooling at the end, has it done any softmax yet?
Pooling here, I think only does.
Oh, here we go. Sorry. So it does the embeddings, then it does the GNN, then it pools, and then it creates the output. Okay. This is like the ReLU or whatever the output activation function is.
This is just a standard linear, I think, self-linear, and there is a ReLU somewhere after that.
Oh.
Self.linear, which self.linear is defined as something else.
Well, it's just a standard linear
torch linear. Okay.
Method.
Yeah. There doesn't seem to be. Oh, I know why. I think because this is predicting a number. It's predicting a regression, right? It's not a classification. Therefore, no softmax. So it's predicting raw logits, right? Yeah.
Right. Okay. Scalar outputs.
Yes.
With the pooling, so coming out of the GNN.
So pooling is basically similar to what the convolutional neural networks have, the global max pooling, right? Or the global pooling, you know, X, whatever, mean pooling, max pooling, mean pooling, right? Essentially, it takes all the outputs from all the convolutions previously and puts them into one flat thing for the linear to consume.
And what's the method behind the pooling function?
So in here, I think we're using global mean pool here, right? And if you go, if you look at this block where it says class GCN graph, right? And in the under init, there is your code here. So self.pool equal global mean pool is what I put in.
Oh, I see, yeah.
And there is a PyTorch read the docs. So that tells you what the different kind of pooling layers are.
Oh, got it.
What I got out of it is that essentially it's a graph equivalent of the global max pooling or global, you know, X pooling in CNNs, right? Okay. So it basically does it across all nodes and creates one single vector for, you know, for your linear layer at the end.
Okay.
The one thing though, I'm surprised, it's a linear layer. So all it does is a linear, you know, it just rotates it, right? So it, I would think there would have, you know, some kind of non-linearity to, you know, would have been nice, I think, but you know, I don't know. It didn't ask, so I didn't actually think about it then.
Yeah, I'm trying to still kind of get my head around just what is getting encoded. The features getting encoded. I don't care really what it does because it's in a network, it's in a training loop. I'm sure that's magical stuff, but okay, so the pooling basically something will rise to the top from the pooling, something meaningful.
Essentially, it takes all the output from all the nodes in your graph and converts it into a flat vector that is suitable for input to the linear layer.
Okay.
Just an adapter.
I got it. Okay. So then it's just a normal.
Adapter, and it does, this according to certain rules, right? It pools according to certain rules. So in here, we are using mean pooling, I think. And then there is, if you go further down where they say extra credit, they also ask you to do, where is this? Two other global pooling layers. And for that, you can use either, it's really, you just replace the pool with something else. So I use max pool and add pool. So sum, if you remember Leskovic talking about it, that the sum pooling is the best kind of pooling because both max pooling and mean pooling have, error or cases where it cannot handle properly. So that's where these two things are.
Cases where it just doesn't make sense or something. I forget. Yeah, I remember hearing.
Yeah. I put it on Slack at one point. I did some, I kind of looked deeply into it at one point. Not deeply, kind of.
Where do you actually put the pooling? Change it. Where do you?
Okay, maybe I put it on the deep learning thing. Hang on. Oh yeah. Okay, so let me point this out, right? So I'll copy the link and put it in the CS224 channel.
Okay.
224 channel here. Here.
Boy.
Yeah, I was, so because I'm taking both courses simultaneously, we are also covering graph CNNs on the other one. And so this came up kind of tangential. So I had seen this example in our class. So I basically, wrote it up for them.
This is talking about the pooling?
Yeah, different kinds of pooling, yeah.
All right, okay. So that's just, somehow aggregating data in a certain way.
Yes.
Flattening it, and then it's passed into the normal linear layer, and the output then is just used as part of the cycle,
exactly.
part of the training cycle.
Right.
Okay. Well, that I feel a lot better about Colab 2 than I did, a day ago, because I did have to get someone's answer and work through it.
Right.
I tend to learn a lot when I have to tease out errors, but this is some of these tools are just so complicated that I'm getting stuck in the mud.
Right, that's true.
All right, so let's see what we got next. So we really aren't necessarily touching on the lecture material, but I think the week that we have a collab in our, like final thing, we might just be good to spend time on just that, and maybe not so much on the lecture material.
I find working through the collabs really helpful.
It is. Yep. So, but you could almost spend the whole time working through mechanics without. But I do really get a lot from the lectures, but I feel like the lecture material starts to go way out into theory land.
Yeah.
And
Actually, for 11 and 12,
Mhm.
this has to do with knowledge graph expansions. So in case any of you guys are actually interested in that area, it's kind of a side area in kind of an application of graph neural networks.
Mhm.
But in case you guys are interested, I would recommend watching the lectures.
Yeah,
They're
yeah.
really good. Yeah.
Knowledge graph is super interesting. The whole realm of ontologies is very interesting, and I'm sure that's a big part of what you get involved in at Elsevier.
Yeah.
The whole realm of knowledge and ontology is just fascinating.
Yeah,
And
there's some very nice ideas here where you can basically, it's self-supervised learning most likely, so essentially you take the existing ontology and you use it to create embeddings, and then you use the embeddings to now do link prediction or graph classification and so forth. It's like pretty good, really good. Yeah, good stuff. Yeah.
and existing
नहीं, भूख ऐसे
ontologies
नहीं लगा है मुझे।
are
हाँ वो मैं
generally
ठीक है, हाँ खाना है तुम्हें खाना है तो खा लो ऐसे बिल्कुल।
existing ontologies are published or at least well known.
Well, I mean, we have our own, but there are definitely, like there's what's that called freebase and
Okay.
there's-
Classic ontologies. Yeah. I just you can do so much with when you start getting into that. If you start thinking about, like you said, new predictions of a new entry, where does it belong in the ontology? And doing good ontologies can be done for so many things. Import classifications of like I work with another group, and there's a woman who has a challenge of classifying invoices for the import-export classifications. And it's a lot of NLP, but it kind of has the same concepts.
Exactly. Yeah.
For next week, are you guys planning to work through homework 2? I mean, we could put that in a collab and share it, I guess. It doesn't exist as a collab right now. Is that right? So by 31st, that's the kind of schedule we're trying to stick to?
Yeah.
Yeah, I'm probably going to make it go to 15 because that's when I have time. Getting 2 lectures and the stuff together is kind of hard. So I pushed it down to 1 week. But that's for me. Yeah, you guys can go ahead. Yeah.
So at the moment, the homework bundles are just stuff you do offline, right? They don't duplicate the collab, because I think aren't we plucking the collab from like a different, like the previous year or something? Maybe they don't quite map onto each other.
Yeah, I think homeworks are pulled from previous years. Oh no, wait, which one is it?
It was the collab.
Yeah, homework from previous year, collabs from this year.
Oh, okay.
Here's this year, and they do have the collabs available.
But it also has homework
Yeah.
out.
They don't have links though.
Oh, right. Okay.
So I think we had to go steal one from a previous year, which was full of material that was not necessarily in the slides.
Yeah.
Actually, I'm looking at lecture 13 at the moment, and actually it's talking about some of the Louvain algorithm and stuff. So it could potentially be interesting to revisit homework 1 a bit later. Or that's what I've been finding.
Sorry, lecture 13 is about homework 1. Is that what you said?
It covers some of the stuff that is in homework 1.
Right.
Okay. Well, should we still kind of try to stay on? This is going to be quite a lot. I'm not sure what I'll have time to literally break into, but homework 1. We've shared a little bit about homework 1 already, right? Sujit has actually done a few of these.
Yeah, I did all the 4 questions, 2 questions I did like as it was asked, and 2 questions I kind of put my own spin on it.
Oh, right.
Yeah, and this would be probably good for next week to make sure we are, but not homework 2. We kind of passed up homework 1. should we just go ahead and try to tease apart homework 2 and see what we get, how far we get?
Yeah,
As well.
I think it will be quite useful. Like homework 2 is quite relevant to the stuff we're doing. So there's one question on like the graph stage and graph attention implementation, and that's one that's more theoretical about kind of the belief. It's like the graphs thing, and then yeah, there's one that's about like expressivity and stuff like that.
Okay, expressive, yeah, that's all useful. Where is the links that we have for homework bundle 2?
I just stuck it in the document. I'll put a little thing down the bottom. So like winter 2019, I guess, has homework bundles. I just stuck that on the, I can put it in here as well.
Yeah, it'll be, I'll end up, thank you.
Yeah, it's a little bit confusing in the Slack because there's like the pin and the channel info and the spreadsheet.
Oh, that was in my clipboard. I had a huge piece of code in my clipboard and it just pasted it. I cannot copy out of Zoom very well. This was previous fall. Okay, so this is where we have, let's make sure we have links. Okay, bam, homework 2 bundle file. Okay, so this will be this will just do a download for me, but at least we know where it is. Okay. All right, well that's, okay, I'm not gonna do that, right? Oh, what the heck, I'll do it for my own benefit.
Submission template is all blank pages for me.
Yeah, I think they just give you like descriptive questions and you're supposed to just fill it up.
Right.
But
I'm trying to archive, unzip that.
Yeah, there's a really illustrative PDF there, and then just the questions, I guess. But this is about enzymes as well. I guess a lot of it's about enzymes. I wonder if it's the same material.
Bioinformatics.
Or
submission template, starter code. Oh, the homework.
that's the one. Yeah, if you look in that, it's all the details.
My machine is so slow. Okay.
I think it's not so much that it's really about enzymes, as in like the enzymes is one of the standard data set. Like if you do
Right.
computer vision, you would come into MNIST sort of thing.
Right. Conditional random fields.
Yeah, this is going to be tough for me to dig into. Let's see. Prove this, prove that.
oh, you can, well, what I do is I do creative reinterpretations of those. Right?
Yeah, you just kind of make up your own outputs. Okay. Just
Yeah,
get in.
I figure, what I think would be interesting here for me, and I just do that.
Just kind of get into the topic a little bit.
Right, exactly. Yeah.
Pull in, try to make models of what it is they're representing. Training loop, okay.
Yeah, this is good stuff,
Expressiveness, aggregation, update.
these PDFs, they're not taken from any publication. These are just custom PDFs they have for the class, I take it.
I
guess.
so.
It does look like it looks like a book, but it's just
Yeah.
because
Just because they're using text to set it, I guess. Nice.
yeah, smart people they do things that look smart. Okay, I mean, this is all the stuff we did talk about in the lectures. So
Yeah, the homework stuff at the bottom, like 4.1, number of nodes, number of graphs in enzymes, looks similar to what we did.
okay, good. I'm trying to just quickly get through training.
And actually, like question 4 is really similar to some of
Right.
the stuff in Colab 3.
Collab
So
3.
I've been hopping.
Colab
back
2,
and-
you mean?
No, Colab 3.
Oh, I haven't looked at that yet.
So kind of there's a few bits when I'm getting stuck on the homework too. I'm just looking at Colab 3 instead.
So would you recommend doing Colab 3 first and then homework 2, or?
Not necessarily. I think some of the earlier stuff, like for example, like question 1 is from like quite a few lectures before.
Right.
So I think they're just, I mean, except for question 4, there isn't like such huge overlap. And I
see.
think they're difficult in their own different ways, sort of thing.
Okay, all right.
Yes, this doesn't look impossible. This looks like things we've done before, sort of. Number of nodes, like you said. Well, that's easy, that part. But you know, actually doing one with GCN, one with GraphSage, and one with GAT, that would be.
GraphSage is like a different algorithm for the PyTorch supports or something. GCN is a graph convolutional network, and GraphSage it's not a different tool. It's not a different library. It's a
it's
just-
another type of network. Sorry. Yeah.
right.
Yeah, it's just kind of different ways of doing the like variations on how you do the message passing and aggregations.
Got it. It sounds like a brand name, like SageMaker or something.
It does. And what's GAT? Same thing, something just different.
Graph attention network.
That's the aggregation or
Yeah. No,
attention?
attention.
Yeah.
I think.
Yep.
GAT. I think. Yeah. I don't know if it's a network or transformer. I don't think it's a transformer though.
Novel neural network architectures that operate on graph structured data, leveraging masked self-attentional layers.
Sage or AT?
GAT. Yeah.
GAT, yeah.
Self-attention, which was the whole stuff about focusing on the things that matter and ignoring the things that don't matter. Attention networks, or attention mechanisms.
Narcissistic networks.
Whatever it takes, yeah.
Right.
Almost like a, okay. All right, well, that's a good, I think, good place to kind of leave it. We know what we have to focus on for next week. It's good luck in doing it.
Yep.
So,
Yeah.
very
It's
good.
getting
Thanks.
harder and harder.
It is. Well,
It'll be
Yeah.
easy next time.
Yeah.
exactly.
It's-
Well, you can ask Wendy. You know, like this is the kind of thing that might take two hits to really feel comfortable.
Yeah.
Certainly fine. Okay, I'll.
Thanks, everybody.
Yep.
All right,
take
thank
care.
you.
Have a great week.
Bye.
All right,
Cool.
you too.
Have
All
a
right.
good weekend.
Yep. Bye bye.
All right,
Bye.
thanks. Bye. Bye.